Hello everyone, this is lecture 26 of the course on principles of behavioral economics. So, we are discussing prospect theory. We have discussed several anomalies that are observed with respect to prospect theory. Then we discussed the editing phase. We are in the evaluation phase, and in the evaluation phase we have, in the previous module we discussed generally how the value functions are constructed with respect to one value scale and one decision weighting scale. So, here in this module we are going to specifically discuss the value function. An essential feature of the prospect theory is that the carriers of value are changes in wealth or welfare rather than final states. So, this basically refers to the concept of reference points that we have been repeating. This assumption is compatible with basic principles of perception and judgment. Our perceptual apparatus is attuned to the evaluation of changes or differences rather than to the evaluation of absolute magnitudes. When we respond to attributes such as brightness, loudness or temperature, the past and present context of experience defines an adaptation level or reference point, and stimuli are perceived in relation to this reference point. Thus, an object at a given temperature may be experienced as hot or cold to the touch depending on the temperature to which one has adapted. For example, in an AC room, if I step out, I will feel that outside is less comfortable or probably much hotter as compared to what I actually got adapted to or habituated to. The same principle applies to non-sensory attributes such as health, prestige and wealth. The same level of wealth, for example, may imply abject poverty for one person and great riches for another depending on their current assets. So, for some individual, by this we want to mean that maybe for some individual receiving a sum of 1 lakh rupees is life changing, while for there are several individuals, or there could be some individuals for whom 1 lakh rupees deposited to their bank account does not even get noticed. Strictly speaking, value should be treated as a function in two arguments: the asset position that serves as reference point and the magnitude of the change, that is positive or negative, from that reference point. The value functions are not identical, they are likely to become more linear with increase in assets. However, the preference order of prospects is not greatly altered by small or even moderate variations in its asset position. The certainty equivalent of the prospect 1000 0.5, for example, lies between 300 and 400 for most people in a wide range of asset positions. This implies that to many people, if they are asked that would you like to get into a bet where you win 1000 rupees with 50% chance or win nothing, or you would prefer a sure bet or sure prospect of 300 rupees or 400 rupees, then most people would be indifferent, right, in the sense that getting 1000 rupees with 50% chance and getting 300 rupees for sure, they are indifferent between these two situations. Consequently, the representation of value as a function in one argument generally provides a satisfactory approximation. Many sensory and perceptual dimensions share the property that the psychological response is a concave function of the magnitude of physical change. For example, it is easier to discriminate between a change of 3 degree and a change of 6 degree in room temperature than it is to discriminate between a change in 13 degree and a change of 16 degree. So, when things are at extremes, or maybe it is concave in the sense when the temperatures are pretty much high, then a change in 3 degree is less perceptible compared to a change from 3 degree to 6 degree. This principle applies in particular to the evaluation of monetary changes. Thus, the difference in value between a gain of 100 and a gain of 200 appears to be greater than the difference between a gain of 1100 and a gain of 1200. So, the difference remains here of 100 rupees only, or say $100, but this is actually, one can also say that this is nearly like from 100 to 200, it is double the amount of gain, but 1100 to 1200 actually gives us less happiness compared to increasing it from 100 to 200. Similarly, the difference between a loss of 100 and a loss of 200 appears greater than the difference between a loss of 1100 and a loss of 1200 unless the larger loss is intolerable for some reason or other. Thus, the value function for changes of wealth is normally concave above the reference point. Again, we have discussed this functional form where concavity implies the second derivative of the value function with respect to the outcome x is less than 0 for any value x greater than 0 and often convex below it, that is the double derivative is greater than 0 for x less than 0. That is, the marginal value of both gains and losses generally decreases with their magnitude. The value function which is derived from risky choices shares the same characteristics as illustrated in the following problems. So, there are two problems. First of all, gamble A and B where the number of participants were 68. The gamble is like you can win 6,000 with a probability of 0.25 and you can win 4,000 with a probability of 0.25 and 2,000 with a probability of 0.25. So, ideally you can see that this also gives a probability of winning 6,000 with 0.25, but then they are broken. Now, 82% preferred this over 18% preferring this one. Now, gamble C and D are like you are losing 6,000 with a probability of 0.25 while there are two alternative losses in gamble D in which in one you are losing 4,000, in another you are losing 2,000, both have equal probability of 0.25. The number of participants 64, 70% preferred losing 6,000 compared to 30% who actually preferred gamble D. Now, from the gambles we derive that, see when we say that gamble B is preferred to gamble A, then this can be written as pi 0.25, that is the decision weights. If I go back to the functional form of value function, so value function is written as pi p Vx plus pi p pi q Vy, right. So, here I have only one outcome. So, V 6000 multiplied by pi 0.25 is less than, it is less preferred. So, that is why this is less than V 4000 plus V 2000 multiplied by pi 0.25. So, since both have pi 0.25, they have been taken common out. And from gamble C and gamble D, what we observe is that pi 0.25 V minus 6000 is greater than, this is preferred to gamble D. So, greater than pi 0.25 V minus 4000 plus V minus 2000. These preferences are in accordance with the hypothesis that the value function is concave for gains and convex for losses. Now, how this is possible? I am going to explain this using this diagram. So, these are the gains 2000, 4000 and 6000. I have hypothetically drawn them. Now, this is a concave function in the domain of gain, concave to the horizontal axis. You can see that this is the utility associated with 2000, this is the utility associated with 6000. Now, if I add this additional utility to here, then utility associated with 6000 would be something like this here, right. If it hadn't been a linear function, then we would expect it to go through this point, but it is actually much lesser than that. Now, this what it was reflected here, that pi 0.25 V 6000 is less than V 4000 plus V 2000, right. So, this is what it shows, that utility associated with V 6000. Alternatively, from this expression you can see that we can always cancel out this pi 0.25 pi 0.25, and then accordingly from gamble A and B I can write V 6000 is less than V 4000 plus V 2000. Similarly, by cancelling pi 0.25 from both sides for gamble C and gamble D, I can always write V minus 6000 is greater than V minus 4000 plus V minus 2000, right. So, here you can see that V 6000 which is actually here, that is less than V 4000 plus V 6000, right. If it is somewhere here, then it actually implies so. Similarly, in the domain of losses, this is where I have V minus 6000. This is where I have V minus 2000, this is where I have V minus 4000. Now, this is minus 2000, this entire is minus 4000 and this is minus 2000, right. So, if I add this much of length to this much of length, I will be somewhere here. So, V minus 6000 ideally should be here if this is a linear function, but since this is convex from this angle, this is convex, and as a result of which my V minus 6000 is actually greater than V minus 4000 plus V minus 2000. Now, these are in negatives, right. So, which means that this is a larger negative, and as a result of which this value is lesser than this value. Okay. So, this is how convexity and concavity are explained in this context. Any discussion of the utility function for money must leave room for the effect of special circumstances on preferences. For example, the utility function of an individual who needs 60,000 to purchase a house may reveal an exceptionally steep rise near the critical value. Similarly, an individual's aversion to losses may increase sharply near the loss that would compel him to sell his house and move to a less desirable neighborhood. Hence, the derived value or utility function of an individual does not always reflect pure attitudes to money, since it could be affected by additional consequences associated with specific amounts. All that is we are trying to say here is that the absolute amount of money probably matter less, and it is other factors that impact the requirement for that money, the loss or gain, that may explain the utility or the value function. So, as previously we have mentioned that 1 lakh rupees coming to someone's account could be life changing for him or her, while it may go unnoticed for a super rich person, right. So, in a similar fashion, we claim that individual does not always reflect pure attitudes towards money, which means the absolute value of money itself does not reflect much, rather the sequential or the situational value is actually more important, whether it is what is the amount of wealth to begin with, how much losses or gains it implies a certain amount of money to an individual, all these things matter. Such perturbations can readily produce convex regions in the value function for gains and concave regions in the value function for losses as well. Kahneman and Tversky proposes that the value function is defined on deviations from the reference point. So, here in this case the reference point is 0. Generally concave for gains and commonly convex for losses and steeper for losses than for gains. So, this point have already been discussed, and several times we try to prove that reference points matter. Now, on the second preposition, we say that it implies diminishing marginal sensitivity, which causes risk aversion in the domain of gains and risk seeking in the domain of losses. The second preposition is that the utility or the value function is generally concave for gains and commonly convex for losses. So, as your amount of gains increases, you become less and less sensitive to further gains, and as a result of which your utility or value function becomes concave. So, the additional gains are not actually generating equal amount of additional utility, rather the additional utilities generated are much smaller. Similarly, in the domain of losses, what they say is that consecutive losses again make us immune to further losses, and as a result of which when we have several losses, the sensitiveness to further losses decreases, and that is why the function or the curve becomes convex. Now, the third proposition says that steeper for losses than for gains. On proposition 3, Katie claims a salient characteristic of attitudes to changes in welfare is that losses loom larger than gains. The aggravation that one experiences in losing a sum of money appears to be greater than the pleasure associated with gaining the same amount. This is actually simply talks about if you lose say 10 rupees or 100 rupees, the pain associated with is much larger as compared to if you gain an equal amount of money, say 10 rupees or 100 rupees. Consequently, most people find symmetric bets distinctively unattractive, and the aversiveness of symmetric fair bets generally increases with the size of the stake. So, what it says is that a symmetric bet is one where the winning probability and the losing probability are same, and the winning and the losing amount are also same. So, for example, we get into a game where you toss a coin. If head turns, then you win 100 rupees. If tail turns out, then you lose 100 rupees. So, Katie says that since a loss pinches us more, then and since both of them this outcome have the same probability, people will not be generally willing to play this game. Now, for smaller stakes, for example, there is 10 rupees, it is only 10 rupees, then you may still find some people who would be willing to play. You increase it to 100 rupees, there will still be fewer people to play. But if the stakes are larger, for example, if the stakes are say 10,000 rupees, then there will be hardly anybody who would be willing to play, because 10,000, losing 10,000 pinches you more as compared to gaining 10,000. So, as a result of which they say that symmetric bets are distinctively unattractive, and the aversiveness of symmetric fair bets, that is the willingness to avoid symmetric fair bets, generally increases with the size of the stake. As stake increases from 100 to 1000 to 10,000, then the aversiveness also increases. Now, what it tries to say here is that let us consider two numbers x and y, which where both of them are greater than 0, then this implies y 0.5 minus y 0.5 is preferred to x 0.5 minus x 0.5. So, basically here x is greater than y. This implies that if y takes a value of 10, then a symmetric fair bet with 10 rupees involved, where you win 10 rupees with a probability of 0.5 and you lose 10 rupees with a probability of 0.5, is actually preferred to say x takes the value of 100, is preferred to a symmetric fair bet where you win 100 rupees with a probability of 0.5 and you lose also 100 rupees with a probability of 0.5, right. This is all it says. Now, this implies that Vy plus V minus y is greater than Vx plus V minus x. See, here we are supposed to, if we write the value function, then of course we are going to have one pi 0.5 here, pi 0.5 here, pi 0.5 here and another pi 0.5 here. Now, we can all cancel them out, all of them gets cancelled. So, we are left with this expression. Now, this can also be written as V minus y, I take V minus x to the other side and Vy goes to the other side, and that is how I have V minus y minus V minus x greater than Vx and minus Vx minus Vy. For y equals to 0, if I put y equals to 0, if you remember V0 equals to 0, and as a result of which for y equals to 0, I will be left with only V minus x and which is greater than Vx, and letting y approach x yields V prime minus x greater than V minus x if V prime exists, where V prime is the derivative of V, this is the first derivative, right. So, what does it imply? It implies that when we are making losses, then the loss function has a slope which is greater than the value function in the domain of gains. So, this proves that the value function for losses is steeper than the value function for gains. The proposed S-shaped value function is steepest at the reference point, which is 0. So, again I bring back that diagram, and here we have this value function which is basically an S-shaped function. You can see that it is concave in the domain of gain, This is convex in the domain of losses. We also see that the slope of this value function in the domain of gain is less steep or steep compared to the slope of the value function in the domain of losses. Alternatively, v prime minus y is basically steeper than v prime x, right. So, when I am making losses, or v prime minus x basically is greater than v prime x. So, when I am making losses, since losses pinch more, so the functional form is steeper as compared to when I am making gains. And the last point that I mentioned in the previous slide is that the value function is steepest around the reference point, which is 0. So, this is the reference point of 0 and the value function is steepest here. This may sound like a subtle tweak, but switching the focus to changes as opposed to levels is a radical move. Kahneman and Tversky focused on changes because changes are the way humans experience life. Consider Jane, who makes $80,000 per year. She gets a $5,000 year-end bonus that she had not expected. Now, how does Jane process this event? Does she calculate the change in her lifetime wealth, which is barely noticeable? No, she is more likely to think, wow, an extra 5,000. So, what it implies is that it is basically 5,000 is compared with what she makes annually, like 80,000. Now, what is asked is that, does she calculate the change in her lifetime wealth? So, in her lifetime wealth, it can be actually a huge amount, can be say 100 times or 200 times more than what she makes annually. So, this is her total wealth, right. What the neoclassical says, we may come back to that point while discussing specifically mental accounting. We say that neoclassicals assume that whatever comes, whatever additional income is generated, that is basically combined with the total wealth that an individual earns in his or her lifetime, and then it is equally distributed. If this is so, then compared to the lifetime expected wealth, an additional 5,000 is actually nothing, and then accordingly it is not going to give her that much of pleasure. But if it is compared with the current situation, then only it gives her a lot of pleasure, and that is why she would be considering it as, wow, an extra 5,000. The main properties ascribed to the value function have been observed in a detailed analysis of von Neumann Morgenstern utility functions for changes of wealth. The functions had been obtained from 30 decision makers in various fields of business in 5 independent studies. Most utility functions for gains were concave, most functions for losses were convex, and only 3 individuals exhibited risk aversion for both gains and losses. With a single exception, utility functions were considerably steeper for losses than for gains. With this, I come to the conclusion of the current module. We have talked here about the value function primarily. In the next, we are going to talk about the weighting function of the prospect theory value function. Thank you.